For the online people, I'm Indumathi, and this is the lecture 2 of special relativity. So I want to start with relativistic kinematics. So we did a little bit of it, but so I hope all of you have come across the word kinematics. So kinematics means that I don't care what has given the particle the force, right? It could be gravity, it could be electricity, it could be anything. Under a force, the motion of that particle, right? Whatever the force may be, if given the force is of this magnitude in this direction, the motion will be the same. So that part is called kinematics. If you actually want to ask what kind of force was it gravitation or electromagnetism or strong interactions, that is called the dynamics of the problem, and the two together is called mechanics, right? So here we are looking only at kinematics. So we already looked at the Lorentz transformations, and I want to show you today that there's a very big difference between transformation of the space x prime t prime and transformation of the velocities. So we already did transformation of the velocity in only the parallel direction, and I want to explicitly show you how there is a difference between we had, for example, if we had a relative motion in the x direction, then x prime was something special, but y prime and z prime were equal to y and z. Now we will see that uy prime and uz prime are not the same as uy and uz. And can anyone guess why that is? In fact, you've all done relativity, you should know why that is. Why is that so? Why is that so? Because if you look at the definitions, right? So look at the denominator, that will tell you. Somebody answer? So y prime is y, z prime is z, but what about t? T changes, right? And therefore the uy prime and uz prime also change, it's obvious. So let's just compute them now. So let's have the equations again. So what is u x prime? Delta x prime by delta t prime, right? So how would you solve this? How will you solve this? Look at the transformation of the numerator and denominator, right? This is the chain rule. So do you know delta x by delta t? Yes, because x prime is written in terms of t, right? So delta x prime by delta t is known here, and delta t prime by delta t, so the inverse of this is also known over here. So I can write both of them. So what will I get? Let's write delta by delta t, let's write them down, gamma times x minus vt, and 1 by delta t of gamma times t minus vx by c squared. And what is gamma? Is gamma a function of t? No, right? So I can remove the gammas. So I only have, what is delta x by delta t? Delta x by delta t, ux. Is v a constant or is it a function of time? Yeah, it's a constant. It's the boost with respect to the two frames sigma and sigma prime. I didn't write that again, right? There is a frame sigma, there's sigma prime, they coincide at t equal to t prime equal to 0, various things. So v is just a constant. What is delta t by delta t? This is higher mathematics, right? So what do you have? 1 minus v ux by c squared. I am not going to burden you with the remaining thing. You can see that when you have the uy prime, let us just write one more step. Uy prime is delta y prime by delta t by delta t prime. And what is delta y prime by delta t? Y prime is equal to, so this is simply uy by the same denominator, right? So this is, but we can't cancel the gamma now. Now you look at this, and of course uz is the same thing. So whether it's y prime or z prime, they will be the same, right? Yes. Not visible? Why is there no display on the top? You're not displaying it? Oh. Can you put it on quickly? Thank you. Sorry, I was just assuming that there was a display. I didn't even notice there wasn't once. Into this denominator. You can leave the light on, I think, or whichever way, okay. Fine. Okay, which one, is it okay? Do you prefer this? All okay? Very good, okay. So you can see and the same thing as I said for Z also, it's the same thing. So you notice two things. One, of course that they are not the same. Uy prime is not equal to uy, that was obvious. The other is this gamma in the denominator, gamma is always greater than 1, okay. But you notice over here, what happens here? This is not u, this is not uy, this is ux. Okay, that is because t prime was determined only by ux, and therefore this denominator here, delta t prime by delta t, has only ux over here, okay. So there is a very funny transformation of these, and this will actually have some importance for us when we go on to the next steps, but right now I will leave it as this, okay. And of course you can write the inverse transformations. Inverse transformation, you interchange the primes and unprimes and make v into minus v, right. I am not going to write it, and as homework I am going to write these equations. So if I write Ax as dux by dt etc., then the transformation laws, I am just going to write them, somebody can copy them down and you can do them as homework. So Ax gamma cube will come, you can see how ugly it becomes. And you can see the mixing of Ax and Ay. I just want you to appreciate that. Okay, so please try it out. It's instructive to realize that when you have an accelerating particle in one frame, then the accelerations are truly weird in the other frame, okay, they are completely non-trivial. That's because already you had a mixing of ux appearing in uy, and therefore you can see the derivatives will also have ax and ay and az all mixed up, okay. The only comment you can make is that when gamma is small, a prime is equal to a, and you get back, you know, the force law of Newton from Galilean relativity, right. So I don't want to make any more statements about that. I want to go on to two applications of this kinematics. Both are very relevant, one for astronomy and one for cosmology. So the astronomy one is a very old observation, which is aberration of starlight. So the way to look at it is, this is the sun completely not to scale, and this is the earth going around the sun, and there is a very distant star over here. So let's say that the star is some distance L away. So this is my star, okay. And you can see that when the earth is here, let's call this theta, and when the earth is here, so in spring and autumn as you can see, okay, the position of the star when the earth is here, or when the observer therefore is here, or when the observer is here, please understand that this dot is the earth, so the position of the observer on the earth is very small compared to the orbit of the earth, but you can see that here the earth is moving with some velocity in different directions. So this little change or this full angle change between the two maximum this thing tells you that if you focus on this distant star which appears to be at rest, all the distant stars, they are, you know that the really distant stars form the referential inertial frame according to Newton, right? So they should all be stationary, right? But in the frame in which the sun and the star are stationary, the earth is actually going around, and so if you point your telescope here in spring, then by autumn your telescope will not be looking at the star, right? So this correction that you have to make is the aberration, and that can be computed. Actually you don't need special theory of relativity, you just need to compute using the Lorentz transformation relations. So that is what I am going to do over here. So there are lots of diagrams here just to make it easy for you to see. So this is the frame sigma, so let's call this x and y. Let us assume that the star is here and the observer is at the origin, okay, but the earth here is moving in this position around the sun, right? So it's moving with, let us say, velocity v, which is known, okay, some 3000 kilometers per hour or whatever, going around the sun, and this is the distance to the thing, this is the direction, and its components can be written as, if this is, let us say, alpha, then this is minus u cos alpha, and this is minus u sin alpha. So other way around, no, cos alpha is this, sorry, if alpha is this, then this is cos and this is sin, right? Yeah, if this is alpha, that is alpha, so that is cos and this is sin, okay? And then this is in sigma. What happens in sigma prime? I have to just draw the same thing. What happens in sigma prime? What is at rest and what is moving now? Here, the observer was watching this star. Now the star is moving, so I have to move. Here instead of the earth moving with v, I make a boost minus v. So that observer is at rest in sigma prime. So because it's minus v now, the star is moving with minus v. Okay, so let's call this u prime, and this is, let us call this alpha prime. And this is sigma prime. Okay. So this is actually what happens when I am looking at the star, right? So this alpha prime is really the direction in which my, sorry for the drawing, my telescope must be actually pointed at alpha prime and not alpha, right? So now let us compute it in both cases. What do we have? I want to find the primed quantities given the unprimed quantities, right? And I have the formulae over here. So let me just apply them. So ux prime is ux minus v by 1 minus v ux by c squared. What is the component of, what is the x component of u? That is minus u cos alpha. But what is reaching you from the star? What is reaching us from the star? Light. So what is the velocity? So 1 plus V C cos alpha by C squared. So I get this, right? Similarly, I can write, now you can see this uy prime will also have a role to play. So there will be a gamma over here. So what is uy? Minus C sine alpha by the same denominator times gamma, right? So gamma times 1 plus V by C cos alpha. So I can compute tan alpha. I have here sine alpha and I have here cos alpha. So let me first compute uy prime by ux prime. So uy prime will have a gamma in the denominator. This denominator will cancel with this denominator. So I will have minus C sine alpha by minus C cos alpha minus V. So let's make it all plus. Okay, and I can take out cos alpha. So I'll get C sine alpha by cos alpha is tan alpha by gamma, and I can even take out the C. So I can remove the C, and this is 1 plus V by C cos alpha inverse is secant alpha. So I have a solution for what is the left side? What is uy prime by ux prime? So what is uy prime by ux prime? So I have a solution for tan alpha prime in terms of tan alpha with some secant alpha correction, and now these errors are all very small. So I can write this as approximately tan alpha 1 minus V by C secant alpha. What did I do with gamma? I said gamma equal to 1 because there is actually a number here. The number is the following. V earth is moving around the sun at 30 kilometers per second, which is 3 into 10 power 4 meter per second, and C is 3 into 10 power 8 meters per second. So the V by C is 10 power minus 4. So gamma is effectively 1, right? So I can drop gamma, and because gamma is effectively 1, V by C is small, so I have expanded 1 by 1 plus x as 1 by 1 minus x in the numerator, right? All this is okay, no problem? Okay. So there is a further approximation I can do. I can write alpha prime, since this change is small, I can write it as alpha plus delta alpha. So the change is something delta alpha. Okay. So I only want to find delta alpha. How do you expand tan of A plus epsilon or f of x plus epsilon? You know the Lorentz expansion, right? If I have f of x plus epsilon, it's f of x plus df by dx times epsilon at x is equal to x whatever plus 1 by 2 factorial. I'm only going to keep the first term, right? So what is the expansion for tan alpha plus delta alpha? It is tan alpha f of x alpha tan alpha delta alpha equal to 0 plus epsilon, which is delta alpha, times d by d alpha of tan alpha. What is d by d alpha of tan alpha? Secant squared alpha, right? And I am not going anywhere further, is equal to tan alpha minus V by C tan alpha secant alpha. So you can immediately see that delta alpha is equal to minus V by C 1 secant alpha cancels. Secant is 1 by cos, tan is 1 by cos, so the cos and cos cancels, and I have 1 by c sin alpha. Okay. Now I go to the other 6 months of the year. What happens? The contour is like this, so V is in the opposite direction. So the alpha prime will become in the opposite direction. You do all the calculations and I will tell you that all you have to do is change V to minus V. So let's call this delta alpha 1 and delta alpha 2 is plus V by C sin alpha. So the total change is twice V by C sin alpha. And if the star is overhead, you can, if you have a good imagination, actually what happens is that the star is actually not at rest above you but is going around in a little circle with opening angle delta alpha. Is this clear? Is this clear? So this is the aberration. If you don't point your telescope with this correction, then you will not see the star. I mean, because the star is so far away that this delta alpha correction, you know, now you know what it is. What is the delta alpha correction? If the star is overhead, alpha is pi by 2, sin pi by 2 is 1, so the correction is 10 power minus 4. In what units? Very nice, radians. See, angle is something very funny. It has no units, but it has, it has no dimension, but it has units, right? So you have to always be very careful about it. So this aberration of stars has actually been experimentally verified. So next, we will go to Doppler effect. So all of you who are interested in cosmology or astrophysics know that we have observed that the universe, every point in the universe is receding from every other point in the universe. And the way we have actually found that out is because you have learned about spectra, right? We know that the hydrogen in the sun gives specific line spectrum. You have learned about Fraunhofer, whatever, all those things are already done, fast forwarded. So when the star is receding from you, then these lines Doppler shift into lower wavelengths and these are called redshifted, right? That is the Doppler effect. There is also a classical Doppler effect, and classical meaning Galilean or Newtonian Doppler effect, and there is a correction coming from special relativity which also has been observed. So that you again have a proof that special relativity holds. So let us go over what is Doppler effect. Okay. So earlier we had the velocity of the earth because it's going around the sun causing aberration in stars. Now it is the source, which is the star itself, moving with respect to the observer, which causes the Doppler effect. So I hope you understand the difference between the two. And the star can be, well, we see the stars receding from us. They need not recede. They can also go in the transverse direction. And you would have learnt in BSc that when they go in the transverse direction, there is no Doppler effect, right? When they come towards you, the frequency increases. When they go away from us, the frequency reduces, which is why the most irritating thing is to have a car overtaking you, so approaching you from behind and honking because the frequency is really, really high, okay? And I wish everybody would learn Doppler effect because of that and not honk, you know, so. Okay, so where are we now? Okay, so the same thing, maybe I should have just left the diagram, but the star is in, okay, let us write it. So now the motion of the star itself or any source of light or sound or whatever, everything is going to tell you that there is going to be a difference, right? So now let us put the star at rest at the origin, right? That's x equal to y equal to z equal to 0 or x prime equal to y prime equal to z prime equal to 0, because we are going to be always at rest is sigma prime, right? Observer is in sigma and the guy who is going is in sigma prime. So let him emit or her emit or it emit a frequency nu prime. So there is a line spectrum. You will expect to see a frequency nu prime in your spectrometer. So in order to understand this, I don't know if I have written this. Okay, maybe I will come to it. Let me first set up the problem, then I will tell you what it is. So this star is emitting light, which we can think of as waves. We know that photons are particles, but light is also has a wave nature. And we can assume that maybe either the crest or the trough of the wave we can call an event, because we have to define what an event is, right? So here I have chosen to call the crest of every wave. So every time a crest reaches me and I observe it, I call it an event. And you remember again, the event is independent of coordinates, right? So these events keep coming. So first event comes, second event comes, and this, let us assume the star is moving away, or the source is moving away from the observer. Where is the observer? Observer is at rest at O in sigma. Okay? So as far as the observer is concerned, star is moving away with velocity v. I hope that v and nu prime are not going to confuse anybody. Okay? So let us say that I emit something at t prime equal to some let us say 10 seconds or whatever, and x prime equal to 0 because the star is at rest over here, and I am receiving the signal at some x and t value, right? What will it be? We are tired of this, we know exactly what this is. This is what we have. But now we are sitting in the origin, so suppose I have t prime equal to 0. When t prime equal to 0, t is equal to 0 because we have coincided our origins at t prime equal to t equal to 0. Let us say that at t prime equal to 0, this first wave was emitted, but that is observed at a point x in sigma. So when will it reach the observer? The observer is at x equal to 0. So this wave which was emitted actually at x prime equal to 0 and so at t prime equal to 0 when t equal to t prime is actually sitting here at x, and it has to reach the observer, and it is travelling at a velocity c. So what time does it take to reach the observer? It's called, let us say, t, time taken to reach observer who is sitting at O, right, is simply equal to x by c. Because it's moving at the speed of light, the wave is in x, it has to reach 0, so it will take time x by c, right. So that means the time taken, total time taken, because already time t has elapsed. When it is reaching x, the time t has elapsed, and a further time x by c will elapse. So the total time taken to reach the observer, which I call capital T, will be small t plus x by c. Is this clear? See, now we are doing something different from before. Earlier we were not asking how much time will the information take to reach us. We were always assuming that if something happens at x prime, there is an observer at x prime with a clock, right? Now we are not saying that. Now the observer is fixed in the origin. So wherever the light is, it has to reach the observer. So you have to add that extra time. So this is the extra effect which gives you the Doppler shift. Now you can substitute everything, right? What is a t? Here t is gamma t prime. What is x? Gamma v t prime. Substitute everything, you will get some, let us just write it. So this is gamma times t prime plus v t prime by c. So this is the first wave. When will the second wave come? When is the second wave emitted? I have emitted the first wave at some t prime. When is the second wave going to be emitted? After? After what is one time period? Very nice. So after 1 by nu prime, so the next wave, which one I can remove this, I think. Actually, I don't need the aberration anymore. So next wave at t prime plus 1 by nu prime, right. So wherever you have t prime, I am going to replace 1 by nu prime, t prime plus 1 by nu prime, do the whole thing again, okay. So you will get a time period t at observer, which will be, you can just, it's trivial, t prime plus 1 by nu prime plus into 1 plus v by c, right. For t prime, have substitute t prime plus 1 by nu prime, 1 plus v by c. So what is the difference in the time? This guy, first guy came at t, second guy came at delta t. So delta t is the difference between these two. And you can see that gamma t prime into 1 plus v by c will cancel this. So you will be left with gamma by nu prime into 1 plus v by c. But what is this delta t for the observer? Sorry? When will the next crest hit the observer? In what time? Huh? Yeah, 1 by nu, right? Correct. This is exactly 1 by, see, exactly like the extra time interval here was 1 by nu prime. So for the observer it will be 1 by nu. This is the frequency that he will see, and you can immediately see that therefore there is a 1 by gamma sitting over there, gamma is greater than 1. So when the guy is receding, you are going to find that, you are going to find a longer wavelength or a larger frequency, and that is the Doppler shift. Is this clear? Okay. You can of course do it for the guy coming towards you, and then all the signs of V will change, blah blah. I am not going to do any more. But the interesting thing is what is called this is the standard thing, and this in fact you will get exactly using Galilean relativity. What is different is if you take the transverse Doppler effect. So here we have only taken one dimension, right? Now we assume the star is moving away or moving towards, and we had very simple formulae. Now we will say let the star be moving at some 3 vector v in some arbitrary direction, either away or towards the observer. Then for that we need to do some little bit of notation. So let me get the little notation right. Okay. So the way in which we will look at it is, actually, okay, fine. We will write it like this. So this is your star at P, and let us call these as the crests. Right? These crests are what are coming to the observer. And in sigma and sigma prime, they will be spaced differently, right? So this will be r over here, and there will be r prime over there, and some arbitrary velocity direction will be there. Now the simplest way to look at it is, you look at either this as a plane wave, or a plane wave is just an infinite approximation of a spherical wave. So if you can write the wave function or the wave for the light, you can think of it as a spherical wave. You can write it as a cos 2 pi, and this is obvious, t minus r by c. This distance is r. You started the clock at maximum, so time taken will be r by c. So when t is equal to r by c, you can see that cos will be 0, and that will be a maximum. So we know that in P, if you just emit the wave, it will reach, if you emit the wave at t equal to 0, then after a time r by c it will reach as a maximum, and therefore this is the right thing. And you know that every frequency can be written as cos of 2 pi nu times some time plus some phase, and the phase I have actually fixed over here. And the 2 pi is, of course, I mean, by now you know why 2 pi comes, right? So that is the periodicity. Is this okay? If it is a spherical wave, it is this. If you have a plane wave, you will do divided by r. I don't care, there is some coefficient, okay? I am only interested in the cos function. Now I can write this as, so if you want a plane wave, you put up by r, but as I said, I don't care. Now I can write this as cos of 2 pi nu t minus x cos. I will tell you what it is. I have now put a theta over here. And you can see that that is what will change from sigma to sigma prime. So this is the phase of the wave, right? Phase of the wave. So the first wave reaches the observer. So this guy emits at t equal to 0. So r by c later he gets the first wave, right? So he keeps counting for some time, let's say some time t, and he asks how many maxima has he seen in that time, and therefore he gets the frequency as that divided by c, right? So he will get, suppose his number of crests is, right, this is the number, that is what you are seeing, number of 2 pi n, right, n is the number of crests. And now if you go to the sigma prime, so this is sigma, I won't draw it again, you will get these many crests, right? So you have to just now compare the two of them together. There should be some place to put the duster over here, keep walking up and down. So you have nu times t minus, so x cos theta plus y sin theta by c, and this guy has nu prime into t minus x prime cos theta prime plus y prime sin theta prime by c. Now you remember I had said that every crest is an event which is observed, it is coordinate independent. Now independent of the amount of time, this guy takes amount of time t minus r by c, this guy takes an amount of time t prime minus r prime by c, but you see they have counted the same number of crests, right, because they have counted the same number of events, and therefore these two quantities are equal to each other. Right, is this clear? Is this argument clear? So once you have that, of course, now you have to just crank out the algebra. I am not going to do the algebra. What you will find is that you will get three equations. I am not going to write them down. I am going to only write nu prime is equal to gamma nu 1 minus v by c cos theta. Well, if you want, I'll write down the equations and you can check them out. Gamma nu cos theta minus, they are very straightforward, just equate the two sides, okay, and nu sin theta the first equation is the equation for the relativistic Doppler effect, right? You can see that is the analog. I rubbed it off, it was the analog of what we got, right? Nu prime, we got nu is equal to nu prime by gamma into 1 minus v by c. Now you can see v by c becomes v by c cos theta. So it depends on the angle in which you are going. Okay, now you can see that when theta is pi by 2, cos theta is 0, but still there is a gamma. That means nu prime is not equal to nu, I hope this is clear, nu prime is not equal to nu, but it's equal to gamma times nu. So what does it mean when theta is equal to pi by 2? That means the source is moving in the transverse direction to the line of sight, right? So this is not the Doppler effect, this is the transverse Doppler effect, and this is something that is not predicted by Newtonian or Galilean relativity. So observation of this transverse Doppler effect tells you that, again, this is a evidence for special relativity to hold, okay, and of course it has been proven. So if you take theta is equal to 0, sorry, if you take theta equal to 0, then you will get gamma nu into 1 minus v by c. If you take theta is equal to pi, you will get 1 plus v by c. So that will be the case for source going away from you or coming towards you, right. That is this normal linear or parallel Doppler effect, and in the case of pi by 2 you get gamma times nu. So these are the two examples I wanted to, this is what I wanted to complete last class, which I didn't. So now we are done with this whole motion of stars and this and that. What I want to now move to is relativistic mechanics. So there is, this section is over, there is all clear, right? No difficulty about it. We are not really starting with a clean slate. Okay. So what did Newton say? Newton said, he said many things, but for us right now, Newton said P is equal to mu, kinetic energy is equal to half mu squared. For a particle, so mechanics means we are now looking at particles and forces, right? Particle with mass m and velocity u. Now I can use the Lorentz transformation equations and find v prime or u prime in the new coordinate system, which means that I can find p in the new coordinate system, okay. But before we do this, it will be convenient to introduce the 4 vector notation. So how many of you have seen 4 vector notation before? Okay, very few. Then we will actually go over the whole thing. Okay. So first let us start with the notion of, I want to start with 2 notions, proper time and light cone. So we already saw, I already defined in yesterday's class, proper time was the time in which that object particle is at rest, and every other time interval is dilated with respect to that frame, right. So that was called the proper time, I called it tau. So there is a very important property, yesterday we saw, I wrote already this ds squared is c squared dt squared minus dx squared minus dy squared minus dz squared. So a small change in the length is given by this, and now the proper time is defined in sigma prime when the particle is at rest, right. Particle at rest means all these variations are 0. So dx squared equal to dy squared equal to dz squared equal to 0, which means ds squared equal to c squared dt squared. This is a very special time which is called tau. You remember you saw tau is equal to gamma, sorry, the other way, t is equal to tau gamma, right. So the critical thing I want to talk about is this. ds squared I said is an invariant of that space time. But now you can see c is a constant, and therefore the proper time is also an invariant. So the difference between t and tau is actually very deep. T is something that transforms from frame to frame, and that is the whole problem about clocks and synchronization and various things. But tau is an invariant, right? So this is something that therefore you also want to hold on to, because once you want to write things manifestly invariant equations, then you know that you should not be using t, you should be using tau. This is the first hint that you get, right? The next thing I want you to, before I come to 4 vectors, so therefore if you want I can write d tau is dt by gamma. So intervals, so t2 minus, if I integrate both sides, t2 minus t1 is equal to from appropriately whatever is in that frame. Now I want to come to the notion of a light cone. I already referred to this but not in, so again this is my 3 dimensions x, y, z, which I cannot draw, and this is the time t, and I make it a distance by calling it ct. So this is my 4-dimensional space time. Its components are ct, comma x, comma y, comma z. Now because this actually codes for r, x, y, z, everything, so you can see that any vector here will satisfy t squared minus x squared minus y squared minus z squared equal to 0, 45-degree angle. So this vector is the light-like vector. So all these are light-like vectors, and since there's actually 3 dimensions, by the way this circle is only in 2 dimensions, but you should imagine, really imagine something, a cone in 3 dimensions. Okay, so this is called a light cone. So that means the surface of this is what light will travel in. Suppose I'm here at this point, this is my present, I am here at O, then this whole thing is my past, this whole thing is my future, and this can only be reached if I can send signals greater than the speed of light, and technically this is called elsewhere. Several decades ago when I was in MSc and I was taught this, the teacher was saying that, so all the students who are dreaming in class are elsewhere. So I think it's very appropriate because you're not causally in the past or future of that teacher, okay. So any point in the past could have been your past, and any line in the future could be your future, and so that is called the world line of the particle. Something, sorry, it has to go through you because your present is here, it has to go through the point 0, 0, 0, 0, 0. It has to lie within the light cone of the past, it has to lie within the light cone of the future, and this is called a world, this is called your world line. And anyone that you are causally connected to must be having world lines within this light cone. Is it clear? Is this the light cone? Yeah.
Where you've written the particle is at rest.
Which particle is at rest? Where are you talking about? Previous time or the next time?
The left side.
Left side, okay, yeah.
The particle is at rest in sigma prime.
See, the thing is this, you always think of the train is moving, right? The particle is at rest on the train, which is sigma prime. The observer is here, I am the observer, and therefore that particle is moving with respect to sigma. This is always the notation of sigma prime and sigma.
So shouldn't that dx square be that prime?
This is all in the same, oh sorry, okay, this all should have been primes, yeah, sorry. So all these are primes, but by the way, this is true for, yeah, okay, sorry, you're right.
It doesn't matter which prime.
Because right now I just want to define the proper interval. So it's a particular frame in which it is at rest. In general, this is the equation, ds squared is, you're right, but I was wrong, technically wrong in not being careful about the notation. So in the frame in which it is at rest, in a generic frame, ds squared is c squared dt squared minus dx squared minus dy squared minus dz squared. So that was true for a generic frame. In the particular frame where it is at rest, ds prime squared is equal to ds squared because that's an invariant, and that is equal to only d tau squared, c squared d tau squared, okay. If I drop c squared, don't panic, c is equal to 1 in my mind, okay. I'm desperately holding on to it Soon I will drop it. I have actually kept on with it for some time, but I may drop it sooner or later. Okay. So here is the thing. So this is the world line. Okay. Now many things can be done geometrically, especially for black hole problems. It's very convenient to use this picture. So I just introduced it, but I am not going to do anything with it. Okay. So now we want to come to the so how do I define this motion? I am in the 4-dimensional space-time. I can define therefore a 4-dimensional space-time whose coordinates are defined by x mu, whose components are c, t, x, y, z, where mu goes from 0, 1, 2, 3. So that the reason it is 0, 1, 2, 3 and not 1, 2, you will find also books which have 1, 2, 3, 4. But then if you do this, 1, 2, 3 are usual if you have vector x has components x1, x2, x3. So these are simply the space dimensions, so you don't want to touch them. You put the time component over here. The only difference is that when you take squares, you will take x1 squared plus x2 squared plus x3 squared, but then you will have to do a different sign for the time component. So you have to keep track of these minus signs, and that is done by defining certain specific vectors, which I will come to soon. Okay. So this is now a four-dimensional vector. It is called a 4-vector in the 4-dimensional space-time. It has a name. It's called Minkowski space, but it is a flat space. Because when you learn general theory of relativity, you will be talking about gravity, and all spacetimes are curved spacetimes, and in fact the velocity of light or the speed of light being a constant will no longer hold there. So we are strictly in special theory of relativity, where inertial frames move only at constant velocities with respect to each other. There is no acceleration involved. The moment you turn on gravity, there is acceleration, and then you have to wait 10 years, 1915, when Einstein wrote general theory of relativity. So this class will strictly stop in 1905. So now the question is, we had a 3-vector x, and now I want to come back to relativistic mechanics. Can I find a 4-vector analog of p? So I know that there is a 3-momentum p, just like we had a 3 coordinate x. Can I find a 4-momentum p? So that is the question that it will make my life very happy. So now let me write again. Sorry, you will get really bored with this, but now let me write dx naught, and now I am going to use some, because I will have u, and see the velocity is u and the boost velocity is always v, okay, at least in this class I mean. So I will have dx naught prime plus okay, I have written beta. Okay, if this confuses somebody, let me write the equations, and if anyone is confused, we will go over them. Don't want anyone to be left out, okay? Fine, so you remember this is x naught is equal to gamma x prime plus v by c, sorry, plus v t, right? Now I can write it as v by c into ct, and v by c I am calling beta. You remember gamma and beta are the standard constants. So now x prime is called, whatever I written, this is x prime. Let me write t prime. T is equal to gamma t prime plus vx by c. Okay, sorry. So this, please forgive me, I have written the wrong equation. So you can see it's gamma x plus beta x naught, and here it is gamma x naught plus beta x1, right? And the other two are the same. So this is my compressed notation for these quantities. Oh God, where is the duster now? Here. Okay. And I know that I can write dx naught by dt, dx1 by dt, dx2 by dt, dx3 by dt and try to get a 4 vector. Now immediately you see, you know that x0, x1, x2, x3 transform nicely, but t also transforms. So in fact you would rather put a dx by d tau rather than a dx by dt. But in any case, let us start with dx. So if I put dx1 by dt, we know that will give me ux, right? And this dx2 by dt will give me u2 and u3. But we know the transformations of these u's, they are terrible. That's the whole point of starting today. That's why I didn't want to say it yesterday because you would have forgotten it by today. They don't transform nicely. The u's are all really funny. How do the u's transform? If you remember, we had u parallel is equal to u parallel prime plus v by 1 plus v dot u parallel, sorry, u prime by c squared, and u perpendicular was, which had a, u perpendicular always has a gamma at the bottom with the same thing, right, by c squared. And if you look, let me write the one dimensional analog is ux prime plus v by 1 plus v ux by c squared, and uy, let's write only uy is uy prime by gamma into 1 plus v ux by c squared, and you can see that this is ux and not the whole u, right. So you can see, immediately see that if I try to write a 4 vector for the velocities using this, they will not transform like a 4 vector because they have all these horrible components and they don't look like this nice transformation law at all. However, it turns out that instead of transforming u parallel and u perpendicular, if I transform gamma times u parallel and what gamma? Gamma u times u parallel, gamma u times u perpendicular, then this will transform like a proper 4-dimensional vector. Now there is a lot of algebra here, so I will do it for the case when I have the simple x dependent transformation only, and as homework you can do it for the general case. So what is it I want to prove? That ux, uy, uz and dx naught by deta will just give me c, right? So then I wanted to write a 4 vector for velocity which was c times u, and this you can immediately see will not transform like a proper 4 vector, and I am claiming now that if I write a 4 vector u mu which is c times u times gamma u, so gamma c, maybe I could put it specifically as, sorry, gamma u times c and gamma u times u, this will form a proper 4 vector. What is gamma u? When I say gamma here, I mean 1 minus v squared by c squared, where v is the relative velocity between v and v prime. Gamma u is 1 minus u squared by c squared inverse square root, where u is the velocity of that particle itself, right? So gamma u, gamma v, gamma u prime, you all understand what they are, right? So let me take a simple case where it is all moving in the same direction. So there is only u, right? And there is no, the uy prime will just be uy and so on. So there will be no parallel and perpendicular components. So what does this mean? I know that u parallel transforms as u parallel prime plus v by 1 plus, so I forget all this u parallel, u v by c squared. So gamma times u parallel will transform as gamma u times this. Now what does this mean? If this is a proper 4 vector, this has to transform like x naught and this has to transform like x. Is it clear? So what are the transformations? That means now we will take only one component. That means this has to transform like equation 1 and this has to transform like equation 2. That means gamma u prime, gamma u prime is equal to gamma v into, so sorry, dx 1. So let me write the other way around. So gamma u is equal to gamma v into gamma u prime plus beta, what is dx 0 prime, gamma u prime c. And similarly, gamma uc is equal to gamma v into this one, which is gamma u prime c plus beta times dx1 prime is gamma u. Right? Is it clear to everybody what you have to prove? Basically, this does not have the transformation property that you expect from dx, dy, dz. But gamma times that has the transformation property. Okay? And what you have to do is just substitute left hand side and right hand side. So this is the definition. This is what you need. Compare the two sides and show that it will be the same. So actually what you will have to show is that if you can cancel on both sides the gamma v. So you will find that you will get gamma u by 1 plus uv by c squared, which is this, because u prime plus v is already there, right? Must be equal to gamma v, gamma u prime, gamma v, gamma u prime. The rest of it is just gamma u prime has come out as common. I've got it here. C plus u prime is already here because this v prime is actually c, right? So I have to just prove this. So you can easily prove this. I'll give you 3 minutes. Please try to prove this. Yeah. See, it seems obvious because of the equations here that I cannot write a 4 vector which is like this. I had a 3 vector x, I put a time component, I got a proper 4 vector. What do you mean by a proper 4 vector? It has to transform according to these laws. If the d bothers you, then just write x0, x1, and this is our old equation, right? This is the same that we have been writing all of yesterday, right? Except instead of writing t and x, I am writing x0 and x1. So if I now write more vectors, they should also transform the same way. That means the 0 component of this vector has to transform as gamma v times 0 component prime of that vector plus beta times x component prime of that vector. That's why I'm writing it. It's very clumsy, the notation cannot be helped, right? And the u component of that vector, or the x component, let's just call one component x. Okay, then it becomes even simpler. Okay, has to transform like x prime, which is the same object primed, plus beta times the time component, which is gamma uc, right? So you have to prove that this transformation holds. And if you just look at it, but we know what the transformation is because we have worked it out here, right? I worked it out here. So I've written it here again on this side. So we know that u transforms like this. So gamma u will be transforming as, I've just multiplied by gamma u on both sides, right? And now that equation must be equal to that equation. So you just equate it, you will get this. So now you have to just substitute everything and make sure that this is satisfied. And of course this is trivial, that's why I'm not doing it. I mean, because this is C, right? Only gamma u has to transform, that is extremely straightforward. The other one is a little more complicated, but again it's 3 steps. Is it clear? And the simplest thing is to square everything so that you are not doing square roots. And just look at the denominators. Gamma u squared is 1 minus u squared by c squared in the denominator, and these two are also in the denominator. So just look at the denominators. I mean, the denominators have to be the same. And you will find that they are the same. I'll just give you 1 more minute and you can finish it. So to combine this, the 4 vector is u mu, which is gamma u times c comma, and this is the similar to x mu is equal to x naught x, right? So what I claim is that I have discovered one more 4-dimensional vector in this 4-dimensional space-time, which has the proper Lorentz transformation equation or satisfies the Lorentz transformations. So every vector that I find in this space has to satisfy the proper transformation equations, right? Otherwise it's not part of that vector space. So this was defining the vector space. It was very simple. We started out with this because we started out with the Lorentz transformations of space and time, and now I have discovered one more vector. That vector is not c comma u, which seems the obvious thing to do, right? Because if I put time and space, then you can expect that with a velocity I will put velocity and c and I will get the 4 vector, but gamma times that is what is giving you the proper 4 vector. So gamma u here tells you that for every particle with velocity u, the gamma of u is defined as 1 by root of 1 minus u squared by c squared. Okay? So did anyone show this? So you have to show that 1 plus uv squared into 1 minus u squared is equal to 1 minus v squared 1 minus u prime squared. What have I done? I have made the equations very simple by taking c equal to 1 so that you can immediately see how easy it becomes. So left hand side is 1 plus 2 uv, I mean just keep doing it, no, I mean I don't have to do it, it's obvious and straightforward. In 3 steps you will get it, okay. And you can prove that u mu is equal to dx mu by deta. So you remember I had already made a comment that if I, instead of writing the velocity as dx by dt, I define new velocities which are like dx by d tau, dy by d tau, dz by d tau, then you will immediately see that the denominator is an invariant and therefore the numerator transforms like a 4 vector. So this whole thing will transform like a 4 vector. You could have started with this definition and found that these are the components of those velocities. You could have done it either way. For example, if you take u naught, it is dx naught by d tau. What is dx naught by d tau? X naught is t, right? Ct. So let's put c. What is dt by d tau? It's gamma, right? So that is the component. Similarly, what is u1? I'm only going to do one more, I mean. Right? So how do I do this? So please understand one dx1 by dt, again chain rule I am using, right? What is dx1 by dt? Ux, very good. And what is dt by d tau? Gamma. So gamma u times ux. The other one will be gamma u times uy, gamma u times uz. Is this clear? So the 4 velocity that we have discovered, the capital U, is a proper 4 velocity which has the proper Lorentz transformation equations that a vector in this space must have. Okay, is this clear? So now what are the other vectors that we can use? We want, somewhere I rubbed it off, we wanted Newton's laws. So we wanted to find a P. So what did we start out with? P is equal to mu, that's what Newton said, right? I started by writing this. And now this is just a trick. Once you know the answer, there are many ways to derive this. This I find is the simplest. May not be good for MSc students, but it gives you the insight actually into it. So the way you look at E naught is that it is simply some kind of a rest energy. Don't worry about it. It is simply a constant so that we can get rid of some unwanted constants in our relation. So what is it that we want to do? We want to now find a relativistic analog of this, which then has the proper transformation laws of a 4 vector. We want to put it in a 4 vector form. So what is it that we will write? Let's write that in the relativistic. So this is for V less than C. So when V is getting larger and larger, I want to write P as some m times u, where m is a function of course of the velocity, and let me write E as some E times u, and in the non-relativistic limit m must reduce to small m, and since you don't know what is E naught, dE by du squared must go to half m. dE by du squared, because you don't know what is the constant rest energy, you can only say that dE by du squared must go to half m, right? So now I have to find some capital M and some script E so that this holds. And it is extremely straightforward to see. Of course, it's extremely straightforward once you know the answer. And why do you say this? Because you now look at the non-relativistic limit of this. You can see that this non-relativistic limit P will go to gamma mu will go to mu, which is what you need in the non-relativistic limit, and E of u, because now I say this is something I don't know. What do I choose it to be? I choose it to be mc squared. So basically I just get rid of this unknown quantity, okay? Because all you know is the u dependence. See, all that the transformation laws give you is the u dependence. These things will not be known. So you just get rid of it by saying that I have a free parameter and I can get rid of it. So I will have, this is gamma times mc squared. And therefore its non-relativistic limit is gamma is mc squared. And so if, let me write here dE by du squared. So this has gone away. Where is the u dependence? So what is dE by du squared? Can anyone tell me? Quickly, do it in your notebooks. So E is equal to gamma u mc squared, which is mc squared by root of 1 minus u squared by c squared. So someone tell me what is dE by du squared? Did everybody get this? So what is dE by dU squared of 0, that is when U is equal to 0, it's m by 2. Does it satisfy? Right? So just from consistency we have got this relationship, and now you can see that U is equal to, so if I take gamma m U by gamma m C squared is equal to P by E, or U is equal to P by C squared, right? Sorry, C squared comes in the numerator, right? C squared comes in the numerator. Sorry, if I mix up C squared, it will just be because I don't remember them. And so I can put them together and write E squared is equal to P squared C squared plus M squared C power 4. I have just resubstituted over here. So I have now immediately two statements to make. I will stop writing script E now because now I have got the exact relativistic value. Let me just call it E. So this is the Einstein's mass energy relationship. P squared plus M squared is equal to E squared. So what does this mean? Suppose my mass is very, very large compared to the momentum. So that means this is an energy unit. This is you can convince yourself that these are both energy units. So let us say that M squared is very large compared to P squared C squared. Then I can write this as square root of and I can keep so I have written 1 plus x to the power of half is 1 plus half x, okay, and I can write, sorry, P squared, yeah, that is mc squared plus P squared by, so I have taken out the bracket, I have cancelled one mc squared, so I will get P squared by 2m. What is P squared by 2m? Newtonian, it's the kinetic energy of the particle. So basically what Newton said was that when you are at low velocities or low momenta, then of course nothing happens to this mass, it just stays conserved. The mass earlier is the mass later, so we can just throw it all away and we only look at the kinetic energies, or in fact later if it is not a free particle, the potential energies of the particle. So we are only dealing with this P squared by 2m part, okay. On the other hand, if I have very high momenta, very high velocities, I am in the relativistic limit, then of course I do the other way around. I write this as P squared C squared plus M squared C power 4, and then my mass will be a correction on Pc. So the leading order will be Pc plus, and if you remember for light, E is equal to Pc, right? You remember this because when it is massless, so when mass is small, you get Pc plus something, when mass is 0, you get E is equal to Pc, and you get back therefore this highly relativistic equation for light. Is it clear? So now the meaning of this energy is that depending on this is the exact relativistic form, and you can always get back the Newtonian result by taking the non-relativistic limit of this equation. So now we have now defined this mass and energy. Now I have written almost everything in terms of 4 vectors, and once I write everything in terms of 4 vectors, I know that all 4 vectors will transform correctly under Lorentz transformation. So if I can write an equation which contains only 4 vectors, then I say that that equation is manifestly invariant under Lorentz transformations, or manifestly covariant. Covariant means if it has an x mu on the left hand side, it will transform as x mu on the right hand side. If there are indices left over on the two sides, then it is called covariance. If it is an invariant, it is called Lorentz invariance, okay. So it becomes very simple for me, I do not have to prove anything. If I can write the equations all in terms of these 4 vector notation, then I am through. It will be all obvious that these transformations will happen. But to do that for electrodynamics, which is the second part of my talk, we have to do a little more work because there are some more invariants and covariants and vectors that we have not yet talked about, because we have not even talked about electrodynamics. We have only talked about kinematics, right? So before we introduce all your electric and magnetic fields, I will give you a small introduction to some mathematical properties of these vectors. That is the Minkowski spacetime. I didn't want to write Minkowski's. Okay. So we already saw two vectors. So we saw two vectors, x mu and u mu, right? Now you see I was a little careful to write the index on the top. Okay, and that's because these are called contravariant vectors. If I have a contravariant vector A, let's forget mu and give it alpha for a change, then I can write under a Lorentz transformation, again you know A goes to sigma prime, this, that, under a constant velocity v, all that is known, but mathematical content of this transformation will be that A prime will be related to A, we saw x prime was related to x mu prime was related to x mu, and the coefficient here will be related to d by d. So let's write the notation little carefully. So here if I have a prime, okay, now you see the prime is on the top here, prime is on the top here, alpha and some beta and beta. So the objects, primed objects in the sigma prime frame will be related to the objects in the sigma frame with this prefactor. Whereas you have another vector called a covariant vector, let's call it B. So this whole part is from Jackson. In each edition he uses different notation, so I don't know which version this is. I have some very old notes. Now let me just write dx so that you can see the quantity. Here alpha and beta were both on the top, here alpha and beta are both on the bottom. Okay, you can see that alpha and beta match. Okay, and so what is the difference here? This is x prime by x, this will be x by x prime. So you have alpha, beta. So this is little subtle, you have to get used to it. So stare at it for a while. Contravariant will be written above because x prime is above. Sorry, one way of remembering it. Covariant will be written below because the x prime is below. Okay? Fine. So this will be, for example, if I take alpha is equal to 0 and beta equal to 1, this will be dt prime by dx, right? And this will be dt by dx prime. And you can convince yourself by applying it on those relations that this is true. Okay, so just go back to your x prime and x relations and find that this will be true. Fine. Now you can write many more things. Once you have a vector, all mathematicians will know that once you have a vector, you will also have a tensor, right? So what will a tensor have? It will have two indices, right? A tensor will have two indices. So I will write a contravariant second rank tensor called f alpha beta. Now who can tell me its transformation? So if I transform it from a prime to an unprimed frame, a contravariant tensor will go to a contravariant tensor, that will never change, right? What will be the coefficient? So I will for alpha what was the transformation? I had x prime on the top and x, no I cannot write beta, let me write gamma, right? Now what will I do with the beta? What will I do with the beta? And now you can write it for any dimension. Now you can write it for rank 3, rank 4, rank 155 because it just follows this. For each index, I have this quantity and then times the unprimed vector. Now someone will please tell me how will this transform? Yeah, tell me nice and loud, I can hear a little bit. Dx by? Very nice. Dx prime, let's call it gamma. Okay, then dx beta by dx prime delta, right? And f of gamma delta. Now you see, once I have two indices, I can have one at the top, one at the bottom. Now somebody tell me the answer for this. Let's take alpha first. Very nice, dx prime. Alpha by
Dou x gamma,
gamma, then?
dou x prime beta.
No, beta is below.
Okay, so
Somebody?
dou x delta by dou x
Beta, beta.
dou beta prime.
I think by now you've got the idea. So contravariant means x prime is on top, covariant means x prime is at the bottom, mixed means whatever was at the top remains at the top and whatever was at the bottom remains at the bottom. Okay, fine. So it will also be, okay. So now let us write something here. And by the way, I am introducing the tensors because in electrodynamics, you will get a tensor. So it's not as though I am simply wanting to introduce tensors. I will write a scalar product in 4 dimensions. You know A dot B is AX BX plus AY BY plus AZ BZ, right? So now I will write the scalar product as A dot B, and there's a reason therefore Jackson used upper alpha and lower beta, because A dot B is equal to A alpha B alpha, and now this means that when I have a repeated index, it implies that the index is summed over. If I have A alpha times B beta, I have to tell what alpha is and what beta is. But if I have A alpha times B alpha, it means A0 B0 minus A1 B1 minus A2 B2 minus A3 B3. Is it clear? So therefore this means is actually implies I will write it only once, sum over alpha, A alpha, B alpha. And by the way, you will find you can prove this for yourself by these laws, that is also equal to, it doesn't matter which way you add, covariant times contravariant or contravariant times covariant, both give the same answer for the dot product, and that will be A0 B0 minus A dot B. There is a very special tensor which is called the metric tensor, G alpha beta, which is the same as lower G alpha beta. Now alpha beta is, alpha has 4 values, beta has 4 values, so you can think of it as a 4 by 4 matrix, right? This matrix is completely diagonal and it has entries of 1, minus 1, minus 1, minus 1. And this is because you have Minkowski space. You can immediately see that when I am multiplying x alpha into x alpha, you can write it as x alpha, sorry, let me write it, x alpha is the same as x alpha g alpha beta times x beta. I know what is x alpha x beta, and g alpha beta I take from there. So it will be x0 squared into 1 minus, so plus x1 squared into minus 1 plus x2 squared into minus 1 plus x3 squared into minus 1, and this will simply give me the invariant. So this is invariant, you can prove. So for x squared, it will give me c squared t squared minus, so let's call x squared as x mu or x dot s minus x squared minus y squared minus z squared. So it will give me this invariant, right? You can see that here. So this is a very convenient thing. You can see that it can convert x alpha is equal to G alpha beta X beta. So the metric tensor can convert the contravariate into covariate and vice versa. And because it has these signs, you can immediately see that if I write X mu as Ct XYZ, then X lower mu, the covariant combination will be minus X minus Y minus Z from this definition. The minus comes from here, right? So what is so convenient about writing this? When I want to square a quantity, I just multiply its upper and lower components. So immediately I'll get c squared t squared minus x squared minus y squared minus z squared. And so also for every other vector. The time component will not change, the space components change sign. Okay? So now that I have introduced all this, I will now go to electrodynamics. So I will start that from tomorrow. Okay? So this is the little bit background that you needed in order to start, the stuff. So what we have now done is that we have now given a formal name to our four-dimensional space-time as Minkowski space-time. We have now written our Lorentz equation. Now you can see I can combine the transformation of x prime mu is equal to something times x mu, right? This is a 4 by 4 matrix. This is actually the Lorentz transformation matrix. It has nice properties and I don't think I will have time to go over them. Maybe in the tutorial somebody can tell you the properties of this matrix, okay? And it satisfies some nice group theory properties also. So for those of you who know group theory, maybe you'll be interested in looking at that. So I thought that was a little too formal, I didn't want to go in that direction, okay? But that itself is a very nice thing to do. And in fact these transformations, what we have done is, what we have formally done is called boosts, okay? We have done boosts which are when one frame moves with velocity v with respect to another frame. Need not be only in the x direction, arbitrary direction. But you can see that you could have a frame which is rotated with respect to another frame. Okay, so those are called rotations, obviously. Then you can have a frame which is reflected through the origin with respect to the other, right? So all these can come in this matrix. You can have all these transformation properties in this matrix. So when we talk about proper Lorentz transformations, they will not include reflections, okay? And that is again a group property which I don't think I will have the time to talk about. So whenever we say Lorentz transformation, I am only thinking in my mind about boosts which are velocity changes and rotations. I am not talking of reflections. But all of you would have learned reflection parity symmetry is a very important property. Even in quantum mechanics you keep getting it, right? That will not come under the purview of proper Lorentz transformation. Okay, so with these remarks I will stop here. So we will probably, maybe half the class tomorrow we will still have some notation, and then we will talk about Lorentz force law first, that is little simpler. Then slowly we will go over to electrodynamics. So by that time I hope, who has not done everyone would have done electrodynamics, right? So you understand scalar potential, vector potential, so you know Maxwell's equations, right? So otherwise just brush it up. By the way, for those of you who don't know, our library is an open library. It's also open weekends. Those of you who live in Chennai, if you have an identity card from the library, you can always, from your college or university, you can always come to this library, sign in, refer any of the books. You cannot withdraw them to take it home. You can spend all day here and in nice AC comfort, and you can sit down and take any textbook that you want, work it through. If you want some things, please don't tear the pages. If you want some things from that book, you ask the librarian, and in fact they can even Xerox some parts. They cannot Xerox the entire book, it's illegal, but they can Xerox certain parts for you and give it to you. So those of you who live in Chennai, I strongly urge you to take a look at the books sometime during the week that you are here. And if you think that they are interesting, you can come back, and if you're free on Saturdays, you can come back on Saturdays. I think 9:30 to 6:30 or 7, I'm not sure what the timing is. 7 till 7, yeah. So it will be open till quite late in the evening. So even if you want to come from college, you can come and take a look at the books. So those of you who want to brush it up, please brush up your electrodynamics, because we will soon start going at the speed of light, okay? So